Good afternoon. So today we will discuss on surface characterization. That here we will mainly discuss the X-ray photoelectron spectroscopy, Auger electron spectroscopy, and secondary ion mass spectroscopy. Okay. So first coming into XPS, so for that we will study what is surface characterization. Surface characterization means the study of the outermost layer of a material that is only on the top surface, that within that less than 100 angstrom, that from the bulk, that from the top surface within the 100 angstrom length scale, that will generally call it a surface structure. So this surface characteristic can be performed by both electron spectroscopies as well as ion spectroscopies. So if you go for electron spectroscopy, that the first one it comes is X-ray photoelectron spectroscopy or XPS. It is also called X-ray photoelectron spectroscopy. So in that or ESCA, electron spectroscopy and called. So in that XPS, so X-ray will supply mainly X-ray will irradiate it on the matter and electron will out. This is the structure of the matter. Then X-ray will fall on the top surface, and that atomic size that top surface length less than 100 angstrom, and X-ray will in and electron will out in case of X-ray photoelectron spectroscopy. Again in Auger electron spectroscopy will go there also electron will be bombarded on the sample surface and electron is out. Instead of X-ray in case of XPS, then in Auger electron spectroscopy it's electron. For electron energy loss spectroscopy yields, there is also electron in and electron out. The electron energy loss spectroscopy that we have already covered during transmission electron microscope. So we will discuss mainly two electron spectroscopy as XPS and AES. The next one is if you go to ion spectroscopies. So generally we use secondary ion mass spectroscopy. Here we have to bombard ion on the surface of your system, and then ions will be out here. So there are other techniques like spotted neutron mass spectroscopy, where ion is bombarded and neutral particles are generally ejected, and that we used to study. So another is ion scattering spectroscopy, where both ion in and ion out is both used in that case. So first coming into X-ray photoelectron spectroscopy, or if we go to the XPS, that the background of X-ray photoelectron spectroscopy is a technique that is based on Einstein idea about photoelectric effect that he developed in around 1905. So it's mostly X-ray photoelectron spectroscopy is based on the photoelectric effect, that interaction of X-ray with matter. So because of that photoelectron generated. So on that technique, it's based on that. And then the concept of photons were used to describe the electron of the ejection of the electron from a surface when photons were fall upon it. Like if a substrate, on that substrate, once you have X-ray photons are irradiated, so some electron is out. So that electron we usually study in case of X-ray photoelectron spectroscopy. So for this, that photoelectron, that Einstein won Nobel Prize so it is 1921 or 1021. So for this discovery of photoelectron effect, and during the mid of 1960, Dr. K.M.B. Sigman and his research group developed XPS techniques. So the first XPS was developed by Sigman, and Nobel Prize he won in 1981 for this discovery. So if you go to the basic information of XPS, so XPS is also known as as electron spectroscopy for chemical analysis. I told ESCA, that electron spectroscopy for chemical analysis. So mainly the chemical composition of a material you can find out by using this techniques, widely used technique, mainly to investigate chemical composition on the surface. So if you see here, so it used for determination of chemical composition, chemical state, electronic configuration of a material. Like for example, for the oxidation state, that you can find out using this technique. So you can see this is the surface, the material, and the blue zone here is the line top surface. That is your the top surface here. So you can see your X-ray beams fall on the sample surface, and electron is mainly coming out from the top surface, the red mark one here. See, this is red mark one here, and then you can see that you will see about 1 to 12 nanometer in case of XPS. So X-ray penetration depth is maximum 1 micron, and the electron is excited in this entire volume here, and then that because of this the electrons are extracted from the surface of that photoelectron we used to study in case of XPS. So this XPS is mainly a surface techniques, and electron moving in a solid can interact with the electrons of the different layer, like in a solid or a crystalline material or in amorphous material. What happens that electrons are present on the on the will go to top surface, electrons are there, so incoming electrons will come and interact with that particular electrons of the different layer, so that on the top surface electron will interact. Then because of this large part of its energy, so that incoming electron or the outgoing electron, that they may interact, and part of its energy or all of its energy will be lost because of inelastic interaction. So average distance, if you see, an electron can propagate travel before an inelastic collision on its mean inelastic flow. That is the average distance that travel by an electron. Like if it interact on the top surface up to certain distance, it will it will come inside. So that the distance traveled by an electron before an inelastic collision is occurred, before it losing its a part of its energy because of the interaction, that is called mean elastic mean free path lambda. Since the energy of the XPS are usually quite high energy in the range of from 50 to 1200 electron volt, the lambdas are very small. Few monolayer it can go inside, and that wavelength of that particular energy, that X-ray is very less lambda. The value of lambda in the sense here is the lambda is penetration depth, so that is very low. So photoelectrons originate from the atomic layer very close to the surface. So that's why XPS is called surface technique, and it's depend upon the surface specificity. So depending on the surface properties, so electron will come out from the characteristic material. So XPS picks the results from the electrons reaching from the surface without any inelastic collision. Like electrons that reaching on the top surface, if there is before that if any interaction, then it will not take. So only the XPS pick results from the electrons reaching the surface without any elastic interaction. And the probability of finding that probability of that emitted electron reaches to the surface, that the electron is coming out from the material should reach the surface, is based on the equation of the depth, that is PD equal to e to the power minus d by lambda. If you see here, there is 1 lambda that here intensity in this case, then 2 lambda that path length of twice 20%, this up to 80%, and here only 9% is 3 lambda. And this curve I can explain here better, you can understand that XPS here 95% of the major electrons originate from the depth of the region of 3 lambda, that is 5 to 10 nanometer only. So if you see the incident beam IS interacting on this sample, and an electron that I0 intensity here that is coming out because of this sorry, I0 is the interaction, the electron, that intensity of the electron is coming, and IS is the electron that scattering that coming out. Then IS equal to I0 into e to the power d by lambda. D is thickness here, and then you can see 0 to 3 lambda e to the power minus x by lambda dx, and you to the whole area you will up to infinity. You will see you will get already 0.95 IS that here. So that means your 95 of the major electron originate from the depth of the 3 lambda here. Up to that depth, penetration depth, you can able to see depending upon the wavelength. So up to that you can able to find out that maximum electron originate from that space. So if you see the photoelectric process, what happens in photoelectric effect, so you have a conduction band and valency band. In the valency band, 1s, 2s, 2p electron. So your core electron is here, 1s electron is core electron. Then because when you have X-ray will come out. So if you see an X-ray falls on this, So if this is the X-ray beam that fall on the core electron, then that this core electron will come out. Because of that X-ray, so this core electron will ejected from the matter, so that will be called as a photoelectron. So electron emitted from the surface with certain kinetic energy by the absorption of X-ray photon. So these X-ray photon comes and this X-ray photon get absorbed here by that material, and then this material because of the absorption, this absorption of X-rays, so those electron will go out, knock out, and here a photon in and electron out because of the emission. So XPS spectral lines are identical to by the shell from which the electron was ejected. Like this electron is coming from 1s, 2s, or 2p, etc. So it's the characteristic of that particular shell from which it comes out. So ejected photoelectron, when it will come out, the ejected photoelectron, it must have some kinetic energy. So that kinetic energy has to h nu, that what is the energy we are supplying, X-ray photon energy that we are supplying, minus binding energy minus phi is work function. So binding energy is here mainly that so that binding energy, this particular electron means that this core electron, so how tightly this bound to the particular cell, so that is the binding energy. So h nu minus binding energy minus phi, then only that is equal to kinetic. That means kinetic energy, that you can see that binding energy equal to h nu minus kinetic energy minus phi. So it has to overcome that binding energy barrier, then only that electron will come out. So mainly because of that h nu, so that A atom is ionized. So electron is ionized, electron emitted from the surface with certain kinetic energy by absorption of X-ray photon. So the electron will come out with has some certain energy. So photoelectron energy mainly depend on the photon energy. So whatever the electron is coming out, so that's depend on the incoming electron which fall here. So this photoelectron and this ejected electron, so they are interrelated. So mainly in XPS, what we study the core electrons. So because that the core electron is an electron that near to the Fermi level. You can see here conduction band, which is Fermi level here, and valency band. Then in electron near the Fermi levels, here the electrons, this is the Fermi level, the electron on the top surface, if you see here valency band electrons, so top surface electron, so they are far from the nucleus. From the nucleus they are far and moving in a different directions, and all over the place will not be carry information about the single atoms. Since it is quite far, so the top surface electron will not give much information. So Fermi level, that is, as you know, the highest energy level occupied by an electron at in solid at 0K. So that is the Fermi energy. So the electron near the Fermi level is far from the nucleus, but the core electrons here, the core electron that here, so those electrons are close to the nucleus. So nucleus is somewhere here, close to the nucleus, and have binding energy characteristic of the particular element. Because the valence electron, the top electron, they are loosely bound, but the inner electrons are tightly bound, and they being close to the nucleus. So that is characteristic of that particular element. So you can able to find out elemental composition as well information about the environment of the atom, like whether it is surrounded by tetrahedrally, octahedrally, or what is the neighboring atom. All those information can you able to find out using XPS. So you can see here we have a core electron here, we have a valence electron here, and this core electron is mainly using XPS to give information about chemical composition and other station state, all these things. So if you go for the binding energy, that binding energy is the characteristic of the core electron. If this is the nuclei here, the binding energy of the particular this will be the mainly depend upon the characteristic of the core electron of each element. So for this particular element, this is the core electron, it has some characteristic. If there is some other element, so their binding energy is different. It is determined by the attraction of the electron to the nucleus. So how the nucleus, the electron is being attracted to the nucleus. So how that force is mainly decide the binding energy of particular electron. If an electron with energy E is pulled out from the nucleus, that particular energy E, if that pulls out from the nucleus, then by attraction with the electron and the nucleus decreases and the binding energy decreases. Like if you remove one electron, an electron with energy E pulled out, the attraction between electron and the nucleus, that will decrease, but the binding energy again it will decrease. So you can see here you have an initial state VAB, but when you have a additional charge, the positive charge, the distribution of electron density, so this is positive. So initial state 1s, both are filled, and the final state, one electron is rejected as a photoelectron. So the binding energy is here E final state minus E initial stage here. So if you see that this is about binding energy except photoelectrons. So what is the Auger electron is there? So Auger electron mainly when the core electron leaves a vacancy, like for example, if this is a because of that incident ray, so this electron goes out. So now you have a vacancy here. So because of this vacancy, what happened? So if you see this vacancy has a lower energy from the top surface orbital, some of the electron will jump to this place, and here because of this, so there will be a vacant will be created here, and this vacant in the next step what will happen? So they with the excess energy of this because of this transition, that will able to knock out the third electron here. You can see the third electron is coming out from the here. So here that you can see a K L1 L2 cells, so Fermi levels here, valency level electrons are just above that. So your because of that it is a 3 electron process mainly. So other electrons are radiation less, so they don't have any radiation. It's mainly due to internal arrangement. Photons are X-ray fluorescence you can use to generate other electron also. When the core electron leaves the vacancy of an electron of higher energy, will move down and occupy the vacancy while raising by the energy heat. So other electron spectroscopy, like how you will define the L electron falls into fill the core level of vacancy step 1. You can see here then KLL other electron emitted by conserved energy released in step 1. So here you can see the K cell, L cell, L2 cell. So kinetic energy equal to EK minus EL2. This particular where is it is there, this particular L1 L2, that is their energy of L2 minus energy of L3 minus work function, that is kinetic energy. So because of this you can see here, so here is there is a vacancy there, and that hole is filled by an tropic electron, and because of this where the X-ray produced, they will knock out this particular electron. So that it is involvement of 3 electron process. You can see here that this X-ray gone or X-ray electron you use in other electron spectroscopy. Here you can see this is the one place, and electron released to analyze here. So because of the electron of high energy that occupy the vacancy of core level, so this is electron of high energy that occupy this, and then because of this electron will jump here, the excess energy will coming out in this case. So in X-ray source is XPS, whereas electron gone is mainly used in AES. So if you see Auger versus X-ray, you can see your probability of this interaction. So atomic number, you can see at low atomic number, X-ray is predominant, whereas high atomic number, that this Auger electron is more. So mainly this probability of the Auger and XPS are correlated by this with atomic number. With higher atomic number, your Auger electronic effect is less. So you can see here relative probability of relaxation of K cell core hole. The Auger electron, that is green curves, are more probable for lighter element. If a lighter element, so this is you can see more pronounced, but for low element, so this is most pronounced. So X-ray yield brown curve, this particular bombardment of the higher atomic energy. So Auger electron yield is released to the fluorescence X-ray yield by omega x by the relation this I omega m is 1 minus omega s. You can find out how this Auger related to the fluorescence spectroscopy. So if you see the instrumentation part of XPS, so XPS in generally either use a single anode or dual anode. Nowadays dual anode XPS are used mainly. The X-ray source is you have a monochromatic aluminum and magnesium K alpha. I discussed in case of XRD that we use either copper K alpha or this copper K alpha we are generally use, or molybdenum or maximum chromium K alpha. But in case of XPS, only two things are available. One is aluminum K alpha, two electron beam. That one there is magnesium K alpha. The aluminum K alpha energy is 1286.6 electron volt, where magnesium is 1253.6 electron volt. So that is the X-ray source need this dual anode, and then you have a X-ray flux unit and narrow X-ray line width. Like here you can see. So this is the assembly that is showing. You have an ion source here, all those things. And because of that narrow X-ray line width and high flux density, so in XPS generally we use aluminum and magnesium, not copper K alpha. If you see copper K alpha energy is very high, whereas magnesium and aluminum energy is comparatively low. So what happened that this in case of X-ray diffraction we use copper K alpha or chromium K alpha, but in case of XPS we use magnesium and aluminum, because here XPS is an absorption process, so electron has to be absorbed there. So the narrow line width because of the absorb of that that X-ray XPS has to absorb inside that material X-ray photoelectron, and then you can see narrow line width and appropriate energy state force these two magnesium and aluminum to be a the anode in case of XPS. So it's suitable for all other elements. You can see here magnesium aluminum anode is there, and you have filament on the top surface and silver substrate and anode substrate. So this way mainly that magnesium and aluminum is used in case of XPS, so because of the narrow line width, appropriate energy, that these two are mainly used in case of XPS over other technique. So if you see the instrumentation part of XPS, so XPS needs ultra high vacuum, where vacuum has to be 10 to the power minus greater than minus 10, torr, or 10 is the order of 8, 10 to the minus 8 to minus 9 torr, and the ultra high vacuum removes the surface contamination and absorbed gas. So it will remove any absorbed gas, if any, in the material, as well as surface contamination that will cure completely removed by the high vacuum. So if you go here, UHP mainly remove surface contamination and absorbed gas. Like in case of XPS chamber, that if there is contamination on the sample surface, that will remove by the high vacuum, and it enables emitted photoelectrons to be analyzed without interference from the gas phase collision. So there will be, being it vacuum, so there will be no collision between the photoelectrons there is no interference effect here with the gas present there. An increase in mean free path of the electrons and photon ions by increasing the ultra high vacuum, we can be able to increase this mean free path, and it prevent arcing and high voltage breakdown. Sometimes high voltage breakdown may be possible, so that will be overcome by this ultra high vacuum. You can see in ultra high vacuum you have a vacuum level 10 to the minus 8 to minus 11, in that such a high vacuum is used. And in ion gun, there is an ion gun in the X-ray photoelectron spectroscopy. Here you can see you have a argon here, X-ray source is coming here, sample is lying here, and you have an analyzer here, electron analyzer, and argon source is there, that ion gun, so that you can use the sample cleaning, as well as if you have a top layer by layer structure, so you can able to see the depth profiling by top surface, by drilling holes. You can able to see the depth profiling, or by argon etching the top layer will be removed, and then you can able to see the below layer, like so on. Or you have a argon plus that widely used ion, mostly for ion guns, like you have a sputtering cycle and analysis cycle, so you can able to see all those information by using X-ray source of X-ray of this particular energy. So then one X-ray is fall on the material, that electron will come out, photoelectron come out. It has to be monitored by a detector, that electron energy analyzer, that lens system to collect the photoelectron, and the photoelectron ejected that they will collect and disperse these emitted electrons accordingly to their kinetic. Depending upon the kinetic energy, which electrons will be separated, thereby measure the flux of the emitted electron in a particular energy. And here two types of electron analyzer is available. One is called hemispherical laser, this is HMA, hemispherical, HAS, that hemispherical analyzer, and you have a cylindrical mirror analyzer that is called CMA. So hemispherical analyzer in that case, so you have a positive charge on the inner plate, like if this is a plate here, on the inner plate, inside plate, you have a positive charge inner plate to attract the electron will be attracted, and outer shell, is negatively charged to repel the electrons. Like you have to balance between this positive and negatively charged. Only electron of specific velocity that can pass through the plate with potential difference. So any electron can't pass through this hemispherical analyzer. So only electron that specific velocity can pass through this process. So then, okay. Then in case of cylindrical mirror analyzer, that is earlier I told, is hemispherical. Yeah, in hemisphere analyzer, it's a hemisphere type, and where and that electron is passed through a potential difference, where electron, the inner plate and outer plate potential is difference, and it's fine. But in case of a cylindrical mirror analyzer, CM has two concentric metal cylinder. You have a two concentric metal cylinder here in with different voltage. You can see here, this is 0 volt. This is positive volt and again 0 volt. So there is a potential difference here. So one of the main cylindrical kept at the position positive at the positive voltage and the other one at the 0 voltage to create an electrical difference between the XPS and Auger electron. So here you can see this is a axial electron gun. That gun can be used in Auger electron spectroscopy. In special case, then because here the electron is full, X-ray is falling and electron is coming out, and the electron you can see because of 0 volt positive 0 volt. So because the potential difference, it will go like this and finally fall on the detector. On the detector here it falls. So electron detector system measure the kinetic energy that you, because of the negative, here the kinetic energy is measured, that h nu minus binding energy minus phi. So once you know the kinetic energy, so h nu so quark function is constant for a particular instrument, so you can be able to find out this binding energy of that one. So if you see here, this is a XPS spectrum. In that XPS spectrum, that you can see the kinetic energy, you have a h nu minus binding energy, phi, from where you will find out the binding energy by from this equation. You can see you have this is a zinc core level like 1s, 2s, 2p, then 3s, 3p, 3d, a valency band, and then conduction band or work from conduction band, and then vacuum level is here. So here the core electron has to, photoelectron to move out of this because of the XPS photoelectron interaction. The photoelectron peaks, here, and you will get a photoelectron spectra, which is discrete binding energy of electrons present in the solid. Like this is a zinc core P that I have shown here. This is the Zn zinc oxide with Mn doping. You can see the bonding from the binding of zinc side and zinc Auger electrons Auger lines, and then particular zinc 2p1/2 and 2p3/2. So if you go for a surface scan and that manganese doping, you are able to see a small here. So XPS peaks are they are very sharp. Whereas if you go for the AES peaks, the Auger spectroscopy, they are quite bold. So it mainly gives the particular what are the elements present by the surface scan, and then if you want to see the manganese particular thing, then you can zoom this region, or you can go for a longer scan to find out that particular zinc is existing, zinc +2 or zinc metal, whatever the condition may be, you can able to see. But if you see here in this XPS spectra, so what is there, that the spectra background is somewhere increasing, so it is not straight line like, so background is step function style. So this type of background is mainly noise that comes from the electron that collide with the electron of different layer. Like you have where the X-ray is coming here, and that X-ray is ejecting an electron here. That electron, what happened? This electron will comes like this and like this and this. So it will go on the way it interact with it collide with other electrons. So before it coming out of the out of the systems. So collision cause a decrease in energy of the electron, and it is no longer remain as a characteristic energy of the element. So because of this multi-interaction inside this body, so what will happen? So that the electron will lose, that decrease the energy of the electron, and it is characteristic, that element characteristic, the energy that particular is lost. So that will mainly contribute to background noise to increase with the binding energy. A sum of all noise can taken from the beginning of the analysis. You can see here, because of this you have a N1, N2, N3, N4 noise. You can see the noise level N1 is here to N2 is here, like this. It's keep on increasing. So that because of this interaction of that inelastic interaction, that electron that collides with other electron collides with other electron of different layer. So that will mainly contributed the noise level of the X-ray photoelectron analysis. So if you go for notation of that particular X-phase peak, that you have to follow some LS coupling rule, where J equal to L plus or minus S. If L equal to 0, the single X-phase peak. If L is greater than 0, double X-phase peak, spin orbital coupling may be occur here. So you can see here that two electrons is there. That if you see the S, that is plus half and S minus half. So J equal to 1 plus I plus half and J equal to I minus half here, because S can able to find out the spin depending upon the direction. So for P, D orbital are observed like P is mainly P1 by 2 and P3 by 2 levels, or D will be D3 by 2 and D5 by 2 by using this S value, and F equal to, in case of F is F5 by 2, F7 by 2, this type of splitting is there. You can see in 2P 3 by 2, so your L is here, that P orbital means the azimuthal quantum number L is 0, 2, 0, L1, L2, L3, L is like here it is 0, 2, 0, the S orbital and P orbital, then D orbital you can find out. And then if we see this zinc example of the zinc 2p, you can see zinc 2 by 2 and zinc 2p 3 by 2. There is a SOS, the spin orbital coupling distance, equal to 23.1 electron volt. So from this, it's required to identify the peak position, peak intensity, and that spin orbital coupling you will get, and then you can identify that particular element. So the information you get from X-phase analysis, that it provides that information from the core level. You will get that binding energy provides information on the chemical environment. What is the chemical environment? How the atomic the oxidation state, how it is shared with other, interact with other elements. So those type of bond information and valence electron density changes, and those type of information you will able to find out from XPS analysis. So change in binding energy of the core electron causes the shift in corresponding photoelectron peak. Sometimes what happens that the photoelectron peak is slightly shifted. So that is mainly the change in binding energy. If a plus metallic state, zero oxidation state, +2, +3, or plus oxidation state, what will happen? So that will able to, the photoelectron peak will be shifted depending upon the environmental the oxidation state of that particular specimen. When atom loses, as you know, there is an atom, when it loses Si0 to Si4, like the valency charges, when the atom loses the valency charge, the binding energy will increase. When the atom gain valency charge, if the atom is gaining a charge, then binding energy will decrease. So you can do one is silicon 0 to silicon +4, and oxygen to oxygen 2 minus. When atom gain valency charge, the binding energy will decrease. You can see here this particular example. This is a silicon substrate. On that you have SiO2 is grown. You can get silicon different oxidation 0, silicon +1, +2, +3, and this is +4 peak. So if you see here that binding energy, when atom loses valency charges, like from S0 to S4, that atom is losing the valency charges S4, but in the binding energy here you can see the binding energy will shifted. You can see here S0 metal is here, then +1, +2, +3, and +3 there. So when atom lose valency band, that binding energy will increase. When atom gain valency charge, so here 0 to +1, +2, +3, they are gaining the charge. So that binding energy will decreases here. You can see another example. You can see here, this is silicon Si2 SiF4, this is silicon here, this is zero oxidation state, then this is +2 state, +4, 2 minus, sorry, silicon is zero state, SiF, silicon fluoride, this is 1 + 1 +2 and +3 or +4. So different oxidation state it exists. You can see when you have a +4, your intensity shift is quite high in that case. So you can see here this is the oxidation state and this is the core level shift at the different oxidation state. You can able to find out that what is the particular element is present, whether it's silicon is a +3 state or +2 state, +4 state, depending on the binding energy peak position, you will be able to find out that. So change in binding energy of the core electron causes a shift. So because of change in binding energy, that the shift will be found that is mainly affect the corresponding photoelectric effect. If you see that information that we get here, you can see XPS surface can provide a qualitative and quantitative elemental analysis of the surface. If this is the surface structure, only the elemental, what is the element is present, oxygen, iron, oxygen, sodium, calcium, the major component. So that will be provided by XPS analysis. So high resolution XPS spectra provide both chemical state surface information. If you go for high resolution, you can give a chemical state surface information. So this is just XPS survey of Fe3O4 coated with glutaric acid. You can see nitrogen is there from the glutaric acid. So those type of carbon is from there. So those type of information you can able to get. So XPS mainly when you go for XPS analysis, the binding energy was determined using carbon 1s peak at 285 electron volt, or some people take 284.6. So the carbon peak has to be, there may be instrumental shifting either from lower binding energy or higher binding energy. So first you have to standardize the data with using a carbon, and that standard reference, or you can use gold AU84, that is also standard. The commonly used is carbon 1s. So that particular I have to, if there is a shift, like this is the carbon position, if this position supposed to be at 285 electron volt, or instead of that it's shifting to 282 or 280 to 90. So in that case what will happen? So depending upon that the CS peak, so if there is any shift, that shift has to comes to here in this position. So carbon is mainly that is here. So you have to standardize. You have to, if it is in this direction, you have to substitute this. You have to add that particular, what if the electron voltage is here, it has to fix this position. If this side, you have to subtract that electron binding energy so that it will comes to this particular position. Once carbon 1s is fixed, then you can interpret all data. So you can see here, this is an example of that protein coated magnetic nanoparticle. You can see here carbon here, or carbon hydrogen, that is fixed at here 285. Then carbon oxygen, carbon nitrogen. Here carbon oxygen, this oxygen and nitrogen, you can see that is the higher binding energy. Because of that, the peak is observed at higher, that because of electronegativity, high electronegativity, that peak is here shifted to in carbon peak at 285 286 something. Then here carbon is the double bond and oxygen, or nitrogen with an oxygen, so there is a more shifting you can see here. So similarly the oxygen spectra, that Fe0, that is lattice oxygen of iron oxide, so that oxygen at 528 or 529, but the carbon oxygen or other, because of the other observed oxygen, you can see, so that is observed at higher binding energy. So you can able to get all those oxidation state, whether by some further fitting. You can see here, this is a Fe3 FeO spectra. That particular spectra was deconvoluted using the two peaks. So that deconvolution using XPS peaks, we can able to see whether XPS from the XPS Fe+2 or +3 contribution, or is only Fe3+, those information you can able to get. If this highly symmetric peak is there, that means this there is no other interaction. So only that particular interaction, that carbon nitrogen is here, So there is no shifting which observed in that case. So, so mainly what you are seeing that effect of electronegativity, carbon, oxygen or carbon, nitrogen is there. So electronegativity play an important role. So like core level, valency level either here, valency level of carbon 2p here and core level is here. Then what happened? So this you can see when your oxygen atom is there. So it shifted the binding energy. So from the carbon nucleus, the binding energy will shifted. So electron oxygen, electron of oxygen atom attraction, that oxygen electronegativity high, so that will pull the electron cloud in that direction. So electron nucleus attraction, loss of electronic screening of that of carbon. So change in local chemical environment of a carbon due to oxygen interaction, how the local environment of the carbon is changing. So those type of characteristics you can able to see. You can see hydrocarbon here, carbon is at 285. If amine CN bond that carbon with attached to nitrogen, it's 286, little higher binding energy. It attached to oxygen, you can see 286.55, or chlorine, fluorine, or it's a double bond. You can see shifting the binding energy towards higher binding energy, towards the oxygen, where oxygen is 532, carbon is 285. So because of that, oxygen electronegativity is shifted toward the 532, towards 530. That means towards oxygen side it's shifted. You can see here that I have already discussed the carbon peak is here, but carbon, oxygen, carbon, nitrogen, you can by using XPS peak fit, like you have to you can able to fit different peaks, and in such a way so that you can able to identify each of these peaks. So by you can use by this peak fitting very easily. So you can see here that the XPS, that the electronegativity is another example, like here zinc oxide where manganese is doped. So a zinc manganese system, here you can see this is zinc Zn peak here. This is highly symmetric peaks in case of Zn ZNO. This is the element of ZNO, that zinc spectra here. That manganese is doping manganese, and if you zinc, that is a ionic radar, if you see they are almost close to each other. But when you go for higher like antimony, bismuth or tin, higher oxidation state here, that here manganese is +2, also here there +3 or +2 or +4 mixture here. So what will happen? The ZNM peak, you can see here the ZN peak are symmetric. So that peak starting goes to tin, it is broadening towards right side, bismuth is broadening, but in case of antimony it's splitted into two peaks here. So Zn M peak broadens and shifts depending upon the electronegativity of M. So if you see zinc electronegativity is 1.65, manganese is 1.55, but in case of tin is 1.96, antimony 2, and bismuth 2.05, and bismuth 2.05. So antimony, because of the high electronegativity, you can see it is capable to splitted that Zn peak here. So change in local chemical environment due to of the zinc, due to doping, so different doping elements, so how it affects to the electron characteristics, so that you can able to find out. So bigger electronegativity of the binding neighbor, larger is the binding energy of the electron. So bigger, higher the electronegativity, your binding energy is can able to see that is splitting and all this behavior you can able to interpret in XPS analysis. During XPS analysis, there is a probability that you will get other characteristic like other peaks, like satellite peaks is you will able to get during XPS analysis. In that case, what happens, like you have a peak here, you can see this in the nickel peak here. So this is nickel 3/2 and nickel 2p 1/2 here. You can see the two additional peak are able to get. So that is satellite peaks here you will able to get. So satellite peaks, that is mainly shake up or shake off, both are due to a sudden change, like an electron, that when the core electron is going out from the orbital, so there will be valence electron here, so it may probability of this electron will interact with the valence electron, so that because of that, due to that sudden change in Coulombic potential, as photoelectron ejected and that passes through the valency band. If the valency band is here, so when it passes through the valency band, so there may be some because of that interaction, so they will able to see the change in Coulombic potential as a result, that shake up or shake off peak you will see. So shake off peak you will see mainly the outgoing electron interact with the valence electron and excite it. When there is an excitation because of this outgoing electron interaction with the valence electron, you will see a shake off that satellite peak is, you will see, instead of Shekar peak, you will see. But when you have a valence electron ejected from the ion, completely to the continuum, it goes out of that particular, from the level, electron energy level. So it appears that you will see a Broden peak in that case. So that Broden peak is mainly, that this is a Shekar peak. You can see, you will able to see here Shekar off peak, but sec of that are called satellite peak. So these two type of peak, here sec off or sec off peak, you will be able to see depending upon the how the photoelectron interact with the valence electrons, and while it goes out from the system. So that you will see. So in addition to that, you can also capable to analyze depth profile using X-ray photoelectron spectroscopy. So like if you have a surface that a bilayer structure, a multi-layer structure, like using that this thin film XRD, where you can you can penetrate the tilting angle one way. Another way is you can do the depth profile analysis by a destructive method. Here you can see if this is a QRXPS space, that sample is here, the X-ray is coming, then photoelectron is coming out. So once the top surface you scan, you go for an argon bombardment. Because of the argon sputtering, the top layer will be removed. Here atoms, you will be remove this top layer atom, and then you will able to see little bit depth. Then again you see here the X-ray, you eject here, and you will able to see that photoelectron characteristic. So layer by layer structure with this type of the depth profiling can be, you can easily see. You can see this is a silicon sample, so this is a silver 3D structure, 3D orbital. You can see when you have a silver, depending upon the, you can see here how from the top surface, and then you keep on bombarding an argon, you can able to see this type of spectra. Once you go more and more, then you'll able to see that particular silicon element composition. You can see similarly silver, you can see at the bottom. So this is another example of that depth profile. You can see here, this is a silicon. It's here on the silicon. You have a silica surface here, and then silica surface of titanium nitride. Then here these two surfaces, Al2O3 is there. Then HFO2 is present on the surface, and then it's glue. So here it is a Al2O3, HF2O2, Al2O based functional stacked on titanium nitride coated silicon substrate. So on silicon substrate, titanium nitride coated, on that HFO2 or Al2O3 is grown. You can see here this is the silicon SiO2 Si layer, then titanium nitride layer here. This one, then you have a aluminum layer and HF layer. All these layer structure, if you have, when you go from the XPS analysis from top, from here to here, and you will see how the elemental composition is distributing. Like for example, if you go for that, for example, this you can see simply titania at the here, or silica at the lowermost side, titania is present. Here you can see initially up to certain depth, you can see that Ti is almost, there is no Ti detection here, 0. So once you reach at this Ti layer here, then you can see there is an increase in titanium nitride. So the last layer is titanium nitride, bottom layer, and on that surface you have a Al2O3. You can see that Al2O3, the red one you can see here. This is that Al2OP, Al2P peak. You can see this is that this in between that Al2O3 here, and the top, since some alumina is on the top surface also, that is initially here. Then there is in between, there is no alumina in this kind of, because hafnium is there, and then you have aluminum. Similarly, if hafnium, if you will see HFO2, you can see this blue, and HF4F peak. You can see it is on the mostly in the center zone here. So HFO2 you can able to see here in the center only. Since Al2, 3 on both sides, is that you are seeing two peaks here, and similarly if you see the black one, the oxygen, is how oxygen is varying here. Initially on the top surface Al2O3 oxygen is there, and then HFO2 oxygen there, then Al2O3 layer oxygen is there. When again you go to titanium nitride, so oxygen level is decreasing. So based on this argon bombardment, you can able to see all these characteristic elemental composition analysis, how they are distributed in the structure of the thin film that you can able to find out. So like the depth profile, you can able to do both constructive, so in the destructive as well as non-destructive way. So this one organ bombardment is mainly this is mainly destructive method to see the profiling of the depth, but that it can be also done by non-destructive method by angle reserve XPS. So you have a sample here, you can see this analyzer, the detector is here and X-ray is coming from here on the sample surface. So here analyzer is 90° here, then you are able to see on the top surface here. Only the X-ray penetration is up to this layer you will able to see here. But when you have tilted the sample, like here you can see the analyzer to the sample, so it's 10° because of the tilting. What is happening that X-ray, you can see the interaction here, it will changes. The more in depth it will go to the X-ray because of that, it's tilted. So you can see that this zone particularly, the analyzer here, this zone is interaction volume here, electron, but here it is like this. So because of that, by tilting the sample, you can do the depth profiling in a non-destructive way. You can see it's a silicon oxide, this substrate on the silicon substrate, the silicon oxide is grown on the top surface. You can see whenever 90° surface, you can only getting the XPS data from the oxide. Here is the oxide data is here when you have a 90° in this case, that the oxide is less in the sense, but you get some material that silicon you are getting higher. But whenever 10°, that here that in this case the profiling will be increased. So what will happen? So that in the earlier initial case that X-ray 90°, that X-ray may be penetrated to the silicon layer, you are in silicon metal, you are getting high intensity, but the oxide is less. But when you have a tilted, so it will go like this. So it's mostly on the silicon layer. So oxide concentration is more here, so metal is less. So this type of using angle reserve, X-ray photoelectron spectroscopy, you can use non-destructive way of depth profiling. So surface signal can be enhanced by decreasing the angle of electron emission with respect to the solid surface. So this is the solid surface, that in electron emission that theta, if you decrease, you will be able to see the core cell structure. So you can see here, this is a silicon nitride. On the silicon nitride surface, this is grown this particular structure, that how this the different angle oxides on the silicon nitride. Like you have a silicon nitride substrate, on that you are growing oxide. You can see here that how this at 90° to you go to 5° takeoff angle. You can see that that nitrogen due to from oxide, that silicon from oxide and silicon from nitride, you can see that nitride peak is decreasing, but your oxide peak, that one is increasing here. So you can see that depth profiling. For example, another example is here. This is an organic LED component, that you have gold substrate, then sulfur, then CH2, then you have CH2O4. You can say this is the molecule, that thiol molecule that present on the surface of AU. They're coated. So you can this silver, gold, then sulfur, then oxygen is present here, then again at the end CH3. In between you have a CH2 is here. So if you see the carbon profiling, you can see the carbon at the top surface here, the carbon is there. Then when you go to this here, carbon is there. But once you go to sulfur and silver, you can see the carbon decreases and then it goes to 0 almost. Similarly, if you see this oxygen at top surface is there, then it goes on decreasing. But if the sulfur at the center, or sulfur, you can see the black one, the sulfur is increasing at the center, which is the middle one. But again, the silver, gold one, you can see gold. There is no, you are not observe anything gold till you reach this layer. Once you reach this layer, then you are able to see that gold peak. So you can able to see this type of structure, the infrastructure information by using X-ray photoelectron spectroscopy. So whatever the data you will get by in addition to chemical identification of silicon or sulfur that present, which oxidation state, that can be determined. In addition, you can able to see some sort of quantitative analysis results you can able to get from this XPS analysis. If you know that peak area, that if this is the intensity, that peak you are getting, you can deconvolute and you can calculate the peak area is there. So if if an element A is present, the peak area of the element A that IA divided by the sensitivity factor of the element, that XPS analysis is that is sensitive to each element. So each instrument has a sensitivity factor corresponding to the element. So that sensitivity factor SA you have to take into consideration. So IA by SA by summation of all element, that AI by SI, you will be able to get that atomic percentage. Like this, an example I have shown here, that carbon, oxygen, nitrogen, and sulfur is distributed. You can see from the surface area I have taken, and then from the surface area, and this is the sensitivity factor of each element from carbon to silicon. You can see that if I calculate the silicon concentration, so NSI, so intensity ISI, that I am getting here, that area, that by sensitivity factor this 1663 in case of silicon, by this sensitivity factor, and then summation of all this, I am getting that what is the percentage of that particular concentration. You can able to find out. So in addition to that, element analysis, XPS imaging is also possible. In XPS imaging, that photographs of the print, you can see this is a print cross section, then you have a clear coat here, then you have a block coat, then adhesive layer is there, and polyelectrolyte below the just below the substrate. So this type of information, how that carbon is deposited at the top surface, you have a carbon, then you have a adhesive layer, how the carbon is distributed on each layer, how the oxygen is distributed, or chlorine, that mainly this bottom coat here, that chlorine is there, so that chlorine, and that then clear coat you have a, you can able to get all the silicon and all those information you will able to get. So carbon scanning, only carbon you can see here, the carbon 1A, CH, C11O. So all those information by XPS imaging is possible by moving sample stage by small X-ray spot size, or by using scanning plate. If you are able to scanning plate, you can attach to the X-ray photoelectron spectroscopy. You can able to see all this type of how an elemental mapping can be possible, that we used to do in case of EDAX analysis. So you can see how this mapping area, if you selected this area, for example, in this mapping area, how this carbon, oxygen, chlorine, and silicon and this all are distributed. So that information you will able to get. So the next we will see the Ajay electron spectroscopy. We'll just take 2-minute break, and then we'll see the Ajay electron spectroscopy. Okay, so now we'll discuss Auger electron spectroscopy. It is almost similar to that of X-ray photoelectron spectroscopy. Only difference in case of X-ray, it is X-ray in, electron out. But in case of Auger electron spectroscopy, it is electron in and electron out. But Auger electron, you also get during your XPS analysis. So in that case, that X-ray in and Auger out is also possible, but that is only in XPS. But if you go to Auger electron spectroscopy, it is electron in and electron out. So electron will come on the top surface, and then you have an electron gone here, and that electron gone from that electron gone, electron will come and interact on this target, and then whatever that this photoelectron is generated during the photoelectron process, you will get Auger electron. So that Auger electron will come to the detector and will accuse its data acquisition is possible. So Auger electron spectroscopy was first discovered 1923 by Meitner, but then it was again independently discovered by 1925 Perry Agar. So because and finally it was named in as a name of Auger, and it was also a surface technique like XPS, and you can get information like elemental analysis, chemical state, depth profiling, quantification, imaging, that scanning of the electron microscope, microprobe is possible. So you can able to both elemental analysis as well as imaging can be possible in this case. You can see here, this is the Auger electron process. That's a 3-electron process, like high-speed electron knock an outer electron out an inner cell electron. So this inner cell electron, so that will come out, and because of this inner cell electron, once that electron come out, so you have a vacancy will be created, hole will be created here, and that hole you can see another electron from here, it will jump to this higher energy electron will jump here, and what are the excess energy, that energy will remove another electron, it will knock out from here. So that is called Auger electron. Here it's a 3-electron process, so it's 1 electron, 2 electron, and 3 electron. 1, 2, 3 electron is involved in this case. And you have elemental instrumentation. If you see that you have electron ground at the center here, that will, from where that electron will come to the surface, general electron source again, lanthanum, hexaboride or tungsten or FeG are generally used here, like a TM and SEM. Same source is mostly same. You can see here as a electron process. This is the ground state is here, that high energy X-ray is falling on this, and this electron is moving out, ejected out this particular electron, and once this electron ejected out, so this is the hole, and that hole is filled by the particular this electron here, so that comes here, then again a hole is generated here, and what are the during this process, that excess energy, that excess energy is removing another electron, knocking out. So this electron is called Auger electron in this case. So this is the photoelectron, and here it is the Auger electron is there. So Auger electron is a radiational less process, and this process of an excited ion decaying into doubly charged ion by ejection of an electron is called Auger electron process. So here only doubly charged ions generating because of this. But you know that minimum, since the 2-electron, 3-electron process involvement here, one electron is coming out here, another electron is coming out here. So it's a total 3-electron process. So that if you go to the isolated this hydrogen and helium, so they can't be detected by this Auger electron spectroscopy. But if you were to lithium, that if it's a lithium atom only, the isolated lithium atom, so that lithium atom, so that is not possible. But when you have a lithium solid, if you see, so there is a bond structure of lithium solid. So in that case, you can able to see that Auger electron spectroscopy can detect that lithium solid, but it's not able to detect the lithium ions, lithium in the isolated atom. Hydrogen, helium, it's not at all possible. And then in case of this, here you can see the nomenclature, that how you can see this Auger electron is named as that this is the core electron, that incident electron is fall here, that is K cell, that K cell is filled by one L1 electron, and L1 is coming here, and then that because of this L1 coming here, that excess energy, that is removing another electron from L2 from here. So the electron is coming out here, that is named as K L1 L2. So because three shell is involved here, so K named as K L1 L2. The three transition process is here. So you can similarly, if it's a K L1 L2, so if it's L1 L2 here, if it's L M1 M1, all are M1, so L electron is coming out, and then M1, then again M1 is knocking out. So L M1 M1, so different type of knocking can be possible. So all different naming are given to this Auger electron spectroscopy. So in the Auger electron spectroscopy, here samples are irradiated by electron gone, that's mostly that electron energy is 3 to 40 kilo electron volt, and Auger electron measures the kinetic energy of all collected electron. So here you measure the kinetic energy, and that kinetic energy you can see intensity versus kinetic energy will measure. This is the example, germanium, aluminum, all this kinetic energy measured. This is a raw spectrum of terbium containing oxide fluoride glasses. So mainly terbium is dubbed here. So this is the raw spectra. So from the raw spectra, what do you to do the kinetic energy versus this that is the derivative of DE, NE you have to plot. So Auger electron of a copper nitride film, in a derivative mode is plotted as a function of energy. So you have to derivatize that intensity. If you see DE by DE into NE, that then you put the derivative you can do, and then you will see that this type of derivative peak. So that from the kinetic energy position, you will be able to see whether it's a nickel, KFF or copper, that can be identified. So for quantification, the reduction of background noise, the derivative data is mainly used in case of AES. In case of AES, that is expressed in terms of kinetic energy, but in case of XPS, it was expressed in terms of binding energy. And by after derivative here, you can able to see that particular element is depending upon the kinetic energy, whether that element is present or not. You can see it's sensitive to light element like barium, boron, carbon, all light element. You can see it says barium is 104 kinetic energy, for sodium is you can see it's 990. So depending on the kinetic energy, so you can identify which type of element is present. Similarly, you can see the chromium, manganese, all type of transition metal, you can able to identify that particular element, presence of the element by Auger electron spectroscopy. So Auger spectra in the different Auger spectra, the differential distribution characteristic, mainly in the differentiation data that you will get. So element analysis by comparing with the standard spectra. If you have a standard spectra, from the standard spectra, you can peak height you can measure from here to here, and that you compare with the standard element in particular corresponding to a particular element, you'll be able to get that composition of that particular quantitative analysis. So relative intensity of Auger electrons can be used for quantification. You can see here, this is the Auger electron spectra. So then that Auger electron spectra, that copper is here, and these are the intensity you measured from the derivative curve, and then that intensity you compare with that of that intensity of the standard element. You can commonly use peak to peak height of differentiated Auger spectra by peak to peak height, that is generally taken. For high resolution, you can use peak area also possible, that can use after background subtraction. Peak area can be used, but most commonly is peak to peak height. You can see here that peak to peak height of some SI for chromium is at 529 electron volt is 4.7. Fe peak for 703 it is here, that is at 10.5, and nickel is 1.5, and then this is the sensitivity factor SI. So you can see percentage chromium I SA by this equation. For you can able to find out the chromium concentration in particular element. Similarly, iron or potassium, iron or nickel, all those elemental composition can be found out if you measure this peak height, and then you can easily find out that from the area from this peak height you can able to find out that percentage. Or if you have high resolution peak, that you can use original Auger peaks can be also used, like here like this the high resolution spectra, so you can able to area under the curve you can also use, but in generally it is Auger electron spectroscopy is used this peak intensity. So here is mainly that the only difference is from the XPS, and here is this 3 electron process in this case of Auger electron spectra, but there it is only one electron is XPS that this electron is coming out. So it's being a 3 electron process, hydrogen, helium, and lithium isolated you can able to detect in this case. And this Auger electron spectroscopy can be further used as a depth profile analysis that can be possible, like electron beam here, then you can analyze area in 0 minute, and then electron beam you applied here, because electron beam the top surface, by using ion beam sputtering, you remove that top surface, then you see the element analysis here. Then again another ion beam, you go to the depth, you can see from this to this and to this, there is a different time you can see able to see by sputtering. So depth profile you can able to see this type of Auger spectra, and then you can identify that from the element analysis. You can see here it is a substrate here, SiO2 substrate, and titanium nitride, titanium nitride is the layer by layer structure. This particular SiO2 substrate, the titanium nitride is grown, and you can see how like XPS data here is also like in the top surface you have a nitrogen, then you go this surface there is no nitrogen, again in this surface there is nitrogen, and then there is so you can see the depth profiling here, there is no nitrogen. And then similarly titania, if you see and the titania on the top surface you are getting that titanium nitride here, this titania corresponds to titanium nitride here, then here is titania corresponds to this titanium, metallic titania, but this is nitride titania is 0. So this type of composition analysis you can do, and depth resolution depends on ion beam energy and the incident angles and surface roughness and what the type of material. Depend upon that your sputtering takes place, and you'll able to find out all these elemental mapping and its distribution. And using this Auger electron spectroscopy, you'll able to also see the combination with this scanning probe. You'll able to see scanning Auger microscopy. The same instrument can give SEM images and Auger spectra, and Auger mapping is possible nowadays. If like you can see the same spectra using electron, you can use that SEM data at 100x and 160x. You are able to see the different grain structure, secondary electron images. You can here mainly showing, and the same sample can be used for those image. The same machine can see the Auger spectra here, the gold and carbon. By electron mapping, you can see the composition structure, like how this particular element here, this particular element is gold here, this is gold, and this is your carbon one. So this one is black one, carbon, white one, gold. So that you can see here, this is the carbon, this is the green is carbon, red is gold. So those mapping is clearly more, better way you can able to see by scanning probe microscopy in comparison to Auger electron spectroscopy. So mainly this both XPS and Auger electron spectroscopy are huge for surface characteristics. So that will give information about oxidation state, chemical bonding, how the local structures, and its quantitative can be possible, as well as imaging you can combine with imaging technique. You can able to see like mapping by X-ray mapping or Auger electron mapping, and able to do all these elemental identification. And then you can also see the depth profiling by either destructive or non-destructive way. We can able to see the solar cell and those type of layer structure, or if that information you can do how that silicon or cobalt or some nickel they are distributed on the surface in the different layer. By layer structure you can easily identify by using these techniques. So now we will discuss the last part, that is secondary ion mass spectroscopy, that is SIMS. That in case of secondary ion mass spectroscopy, here the ion beam is irradiated on the sample surface, and again ion is produced. So here that ion is interacting how the material, so that we will study. So first J.J. Thomson used the prototype of MS he built, so that was on the basis of M by Z, and then MS concept put into practice by Francis Armstrong, who was a physicist of Cambridge in England, 1919. And then the first prototype experiment was on SIMS was at the University of Vienna. In 1940, the first experiment was performed. And then time of flight, the analyzer is in around 1948 to 52. And then the quadrupole come into picture. And finally, at the end of towards 1960, SIMS instruments were developed, in America and Paris. So mass spectroscopy are now one of the most analytical technique that secondary ion mass spectrophotometer. So it's a combination of ion with mass spectra. So based on the mass to Z ratio, you will identify that particular element. And you can see here how it's happened. So the bombardment of sample surface with primary beam ion. So you have a primary beam here. So that primary beam red color. It's showing that ions is falling on the sample surface here. This is the sample, and on that matrix where impurity atom, of this green are the impurity atom, blue are the matrix. And when that ion beam falls on this, so because of this, the bombardment of sample surface with primary ion beam followed by the mass spectrometry of the emitted secondary ion. You can see here once it falls the primary beam, so it interacts with this, and then what happened? Secondary ions are formed. So the secondary ions are isolated by an applied voltage, it is applied to the detector, and then the mass analysis of each secondary, the produced secondary ions is to perform. So you have a primary beam, and then you have a secondary emitted beam, so then followed by a mass spectroscopy analysis. So it is used to characterize the surface and subsurface region of the material based on M by E or M by Z ratio of the ejected particle under ion bombardment. So based on the M by Z, you will able to, or M by E, you will able to see which particular element you can analyze. So it involves energy transfer process from IP to the I sample, and that incident beam, that primary beam, it's coming, it interacts the sample, and then it's coming out at releasing I secondary. So it's a energy transfer is involved in this process, and the characteristic feature of this is mainly used for quantitative chemical analysis, and it has a high detector sensitivity, and you can use 10 to the power 16 to 10 to the power 13 atoms, and it's a large dynamic range here and very high depth resolution. So since ion beams, your resolution is quite, the depth resolution is quite high, and it have a lateral resolution is also good by using ion microscopy. You can up to less than 10.5 micron, you can able to see the lateral resolution. And the important thing that here in ion, secondary ion mass spectroscopy, all elements can be detected. There is no such restriction, so all element can be detected by secondary ion mass spectroscopy. You can see you have a primary ion source, that is ion gone in the top, primary ion source. Then once it fall on the primary beams is generated, it fall on the sample surface, and then that the ions are produced, that ions has to come to the detector. So before coming to detector, you have a ion extractor. So that ion extractor electrode is kept here. You can see these two are ion electron detect ion extractor. So at ion electrode, so that because of the potential difference, that electron will come out and it will go to through a mass analyzer. So this is the mass analyzer here. So this fall on this through the mass analyzer, the electron beam comes and it goes to the ion detector here, and then you have a through you have a vacuum, and then through the vacuum it comes to the ion detector. Once it comes to the ion detector, you can able to see the mass spectra. You can able to produce this type of lines, mass spectra, and then ion imaging can be done, depth profiling can be done, and you compile those data, and then you can also you can get a 3D mapping by using this secondary ion mass spectroscopy. So here primary ion source are generally used in two types. One is either oxygen, O2 plus, that electropositive species they use for, that is boron, aluminum. So this type of oxygen, O2 plus ion beams are used, or cesium plus electronegative species can be used, that is nitrogen, phosphorus, arsenic, it is that can be used. So mostly this type of oxygen, electropositive and electronegative, this type of species can be used for ion source, or even sometimes gallium, that gallium plus is used as a improved lateral source that is used. So here that you can see the primary beam at angle 10 to 60 degree, it fall on this beam energy mainly 0.5 to 20 kilo electron volt, and it fall on the sample surface. So ion extractor there, that is the ion extractor that is kept here and here, that secondary ions are formed at the sample surface, immediately removed by the ion extractor. That ion extractor immediately take out that this the secondary ions, and it take to the transfer that to the spectrophotometer, that is, sorry, the mass analyzer is transferred to the mass analyzer. So you have this five component mainly required, and it you to used in a vacuum. And then the role of the mass analyzer is to to analyze that secondary ion based on that three technique. One is time applied, how these ions are the movement of that the ions with same energy but different mass travel in different velocity, that even though they are same energy, but if the different mass, so they will movement velocity, different velocity they will move. So it measure the time taken to the travel to travel a drift space. So the time of flight is one detector type, that is a simultaneous detection of many elements is possible in that. It is a high transmission, high resolution, and is a very high mass range. You can able to, depending upon the mass of the element, you can identify them by time of flight. And you have a quadrupole that certainly measure M by Z. Certain M by Z will reach the detector for a given voltage, for a given ratio of voltage of the based on the potential difference or voltage, that M by Z will move, and that will do the quadrupole detector. But another one is magnetic detector, that is magnetic sector. So degree of deflection of ions by magnetic field. You apply the magnetic field depending on the M by Z or M by Q ratio, that electron, that particular ions will be deflect. So then under the magnetic field, so that can be used as another mass analyzer detector. So in addition that, you have ion detector. So micro channel plate MCP, there is their array of multi electrons, miniature electron multipliers are there. So what will happen, an ion passing down the channel hits the inner channel wall and produce secondary electrons. So those type of ion detectors are there. You have a and we need very high vacuum, that is essential requirement for the operation of the analysis. So this, without high vacuum, all these electron beam can't be put to the detector. You need, and if there is some other gases in the analyzer, so it will interact on that. So again it will interfere. So you have to be use all this in high vacuum. So the secondary ion yield here, the sputtering of the primary ion, because of the sputtering of the primary ion, we get secondary ions, and the ion yields is the fraction of the sputter ions that becomes ionized. So once that, because of that primary ion, whatever the sample surface get ionized, that fraction of that ionized from the sample surface because of the sputtering, so that is the secondary ion. It's mainly depend upon the element, there is chemistry of the sputtered surface, as well as primary ion. So it's present that the intensity that of the primary ions, and it's on the sample surface, how this surface is a rough surface or smooth surface, or the elemental structure of that sputtered surface. All the technique, that secondary ion yield is depend on that. So oxygen sputtered on the surface will increase the positive potential. If you go for a oxygen sputtered, then positive potential ion increase positive ions yield, whereas the cesium sputtered on the surface increase a negative ion yield. You can see the positive ion yield is proportional. This ratio you can find out. You can see that all that yellow atom, that is saying the lithium to all this nickel and cobalt, all those, but the positive yellow colored, so that used mainly oxygen primary oxygen as a primary positive source. Sputtering primary ions, whereas in case of green one are mainly primary negative secondary ions, that's used for the by the cesium is used here. So variability in ionization efficiency lead to different analysis condition, and elements is indicated on the periodic, like depending upon the which type of element you are going to analyze, you can choose your that primary beam, and you can able to get that what is the secondary ion yield using those questions. So if you see the SIMS secondary ion mass spectroscopy, that you have a mass scan. So using that mass scan, you can able to identify whether lithium, sodium, potassium, chromium, potassium, whatever the element present on particular this your material, depending upon the mass, you will able to see that what is the by the mass scan. In addition, you can able to do the depth profiling, like you have a substrate structure. So first on the top surface, then you bombardly reach out by reaching, then second sputter, then third surface. So you're able to see all those different depth profiling can be possible. So that is here when you go for a depth like dopant diffusion in a semiconductor, at least you have zinc, you have a zinc oxide, you have doping with nickel, cobalt, chromium, like this in this element. this material that this spectra is mainly lithium, sodium, potassium, those type of doped with ZNO. So that this dopant element that you can identify isotope enriched structure. So the isotope enriched structure that the isotope labeling, that those information you can able to get. If organic structure, that depth profile is possible, and impurity or the trace element you can able to identify by using SIMS. And ion imaging, so during this SIMS analysis you can also use the imaging spectra to characterize content of the sample. So what are the contact, characterizing contact on the sample surface, the impurity after processing, what are the impurities created on the surface, and the 3D mapping, chemical analysis can be possible here. You can see the depth profiling here, that is an organic LED structure like same to XPS or AES analysis. You can see on from this to this, you have a titanium on the titanium substrate. It's grown on a organic LED. That how that different dye molecular different this molecular present here. So that can be analyzed by using from, if you go from the top to bottom here, where initially you're able to see this one, this you can see here initial first top surface, the data is coming here. And then similarly if you go to the bottom surface, the yellow one, you can see here, or in the ITO here at the end, you are able to getting that ITO, the gray color, the ITO. So by using the depth profiling, you can able to see all those, mapping can be possible. And here is a detectable element. All element, the hydrogen can be also detected here, greater than equal to hydrogen, you can able to detect here, and detector limit is here ppm to ppb range. And here you have a very good data resolution you will able to get using this spectra, this secondary ion mass spectroscopy. And then that you have a, since you have an ion they are producing here, that ion imaging can be possible, and that ion imaging will be able to lead to the chemical analysis. You can see the composition structure, that a primary beam is fall here and the secondary beam is coming here, and that secondary beam, the intensity recorded as a function of primary beam position. If you record, you can see here like that you can see silicon, then is a C3H6 or nickel is there. So you can see the silicon mapping, this carbon, and all this mapping can be possible. Then you have to combine all this distribution. It's a circuit board. You can able to see how this element, you can see that silicon is everywhere present. Here this is this green, and this here nickel and carbon is here. So because of this overlapping, we are getting a pink color, red, green, and blue overlapping. We are getting, this is the zone where all the three elements are present, but the other element like carbon C3S is mainly present in this area, green area you are seeing. So that depth profile, the image and imaging can be possible. In addition to the depth profile, you can see this is a drug. Inside the drug, you have a sodium is present. So that sodium mapping, if you do, so you can see the sodium is on the surface at the core. So those type of it's a drug composition, which is the sodium containing tablet. So those type of information you can able to get. So mainly secondary ion beam intensity record as a function of primary beam position, and material distribution composition analysis can be possible by ion imaging. So all material distribution you can able to do. So that ion imaging, you can get it, you can use that ion imaging to get a 3D image. So image from the increasing depth can be obtained, and hence three-dimensional data can be generated. So you go for the from depth to top to depth. So what will happen by you see the distribution, how that particular element is distributed, and then you combine all of them in X, Y, Z, all coordination. Then you'll be able to get a 3D structure. You see this is the magnesium, gallium, iron, and yttrium, how they are dropped, and then on the top surface bulk and cross section image you see, and then you combine all of them to get a 3D structure. You can able to map that 3D structure here. So, but in SIMS, there are lots of constraints are there, like you have to choose proper primary beam to so as that the proper second, so that secondary ions are generated. Its detection limit, depth resolution, so those parameters are necessary, and then how they have to go for a high beam primary energy, so that secondary ions can be yield, and the angle of incident, the particular angle you are incident on the sample surface, to you have to go for a particular angle where the secondary ion beams are produced very high. For the depth profiling or depth resolution, to get optimum depth resolution or normal incident you are getting that, or sputtering rate, what is the rate of the sputtering of the primary beam and detected area, the particular area of location you are bombarding, and species monitor that what are the element count rate, so the detection limit that affect here. Energy distribution, that secondary ion energy has to be distributed varies from ion different ion species, so that the energy, because of energy distribution you have to differentiate based on the mass, that also affected by the energy distribution. And also insulator effect, there is when a charging occurs during the analysis of an insulator, the energy distribution can be shifted, so that insulator effect has to be nullified. So you have to take care of all these analysis condition to obtain a better result. So two principal methods of elemental sensitivity of quantification. If you go for a quantification, so you have to go for a ion implementation standard, you have to know a particular standards with a known fluency, so that with the comparison of the standard you can able to identify, or you can use a bulk sample docked to accurately known trace element. When you compare with that, you can able to get that elemental quantification can be done. And there are various profiling issue like ion being mixing, some of the ion being from they may be mixed, so that will call problem. And if there is a matrix effect also sometimes, then surface effects come into a picture, and mass interference. So I have just taken into one mass interference here. You can see this is a bismuth 10 monitoring and if you go for a that is silicon 30, or you can see here you can see that arsenic 75, and this structure here arsenic 75 and this silicon 29 30 and oxygen, so mass is almost same. So here to differentiate that can be by using energy selection. If you take, you can see that spectra here, the arsenic spectra is broadly distributed, silicon is here sharply then decreases. So if you go for a particular energy selection, so in here in this zone energy selection, you will get mainly arsenic one. But if you go this selection area, then what will happen? You will get a overlapping of both those things. And then, like example that you take boron 10 you want to detect, so monitor that here this is not possible. Then you get boron 11. So that isotopic that element you can monitor, and you can see that is 31 phosphorus and 30 Si1H. So in that case, it's almost similar mass, so high mass resolution del M by M. So that resolution you can able to see and to find out that particular element. So it's relatively sensitive factor, that RSF, that conversion factor for secondary ion intensity to an atom density. So that factor you have to go for the known component. You have to know that RSF factor, and then once you know, you are able to do all these elemental analysis. So if you compare these three techniques, XPS, AES, and SIMS, so XPS, as I told, is huge X-ray and more in primary beam, and in case of AES, it's electrons, and SIMS it is used as ion. So here and all these to XPS and AES, so electron energy we measure from the SIMS, that ions, that mass we used to measure. So here is charging is possible. You can use all sample in AES, mainly conductive sample, and here also you can both use all samples, as well as there is a charging issue that has to be nullified. And then this you can see XPS of 10 micron surface area, AES is 10 nanometer, SIMS is 100 nanometer, that area of analysis. Sensitivity almost equivalent, little bit higher in case of SIMS, 0.1 to 1 nanometer. So all element except hydrogen helium is possible in case of XPS. So hydrogen is 1 electron, helium is 2 electrons, so that is not possible to detect, because in case of XPS, except these two all element is possible. In AES is hydrogen, helium, and isolated lithium. So these three is not possible, or all other element can be possible for analyzing. It seems you can analyze all element from all predictable element. You can able to analyze by using SIM spectra. So identification sensitivity also very or less than ppm level in case of SIMS, whereas 0.1% in case of XPS and AEC. So for quantification, you need recurring standards you need in case of XPS, AES, but here you have to very close standard, like you have to proper standard you have to choose in case of SIMS, otherwise it's very difficult to quantify the SIMS data. So molecular analysis is only mostly possible in case of SIMS, and this molecular identification is not possible by XPS and AES. So there are other very parameter like chemical shift here that is coming into picture. XPS and AES also shift, and this type of shifting is not possible. So you'll get direct data from SIMS. So depth profiling is element analysis, chemical analysis, all those is possible in case of these techniques, XPS and AES. And destructive, if you see this non-destructive, only if you spotted it's destructive, otherwise depth profiling can be done in angled resolved XPS, and here in the AES only spotting case it is not destructive. But seems ion beam has to irradiated on the sample surface, primary ion beam is always destructive. So in the today's that lecture we mainly discuss about XPS, AES and SIMS used to study the outermost layer that is less than 100 angstrom, that on the top surface analysis can be possible here using electron spectroscopy. XPS or AES can able to identify the chemical composition, chemical state, depth profiling, as well as XPS or AES mapping can be possible in case of electron spectroscopy. But if you go for ion spectroscopy, secondary ion mass spectroscopy, so you can through the mass scan, depth profiling or ion imaging you can use to construct a 3D structure. And in this XPS or AES, that is there also you can able to do all this, elemental or this mapping, and you will get very good information about this chemical composition. So here XPS and AES mainly use, or XPS you use all element except hydrogen and helium, whereas AES you use all element above lithium. You can use lithium solid band structure you can analyze. So in ion spectroscopy SIMS you can all elemental structure you can use, or you can identification of those quantification possible. So in all my characterization technique or that all class lectures what we studied mainly, so you all diffraction techniques that we cover, X-ray, electron as neutron diffraction, so scattering technique, X-ray and neutron scattering that we have covered, and surface technique like XPS, X-ray absorption spectroscopy or secondary mass spectroscopy. There is imaging technique SEM and TM that we covered. In addition to that, there are many other, this X-ray photo or this ion or electron or this neutron as well as ion mapping using many other techniques are there. So you have to go through all those techniques. It's not possible to cover all techniques. So I have covered what are the most important techniques used for characterization. So you can cover some of these books that for my course that whatever with these slides that is available online with Anuvidya sites that you can go through, and these books you can refer like AR Waste Solid State Chemistry or Advanced Technique by A.K. Tyagi and co-authors, and Elements of X-ray Diffraction by B.D. Quality and Material Characterization by Y. Lang. So all these books can be used. There are free softwares for XRD. You can use FullFlow for your analysis. In XPS, you can use XPS PickFit that's available, PickFit 4.1. So you can use those software for your analysis. And if any of any doubts that during this course or during your PhD or during your master's program, any characterization related issue or some analysis, you can contact me through this email ID. And thank you all. If there is any questions, you can raise now. Otherwise, we'll complete. Question. So XPS that the question is can XPS replace with FTR and EDAX? No, it's not possible. FTR mainly give the functional group analysis, where EDAX will give you elemental mapping, those type of structure. But if you in XPS you will get the information like oxidation state. So that oxidation state information you will not get from FTR or EDAX analysis. So, but if you go for imaging part, that elemental analysis that can be possible with EDAX which you can do with XPS, but the FTR is completely different technique that is based on how that functional group vibration depending upon the based on the infrared radiation. So the FTR is completely different technique, and the XPS can't it can replace that the result that the oxidation state information, though that what is the chemical local environment structure in that interaction. So those type of like if a dopant you are doping some element in another structure. So how this doping element interact, how the surface molecular interact with each other. So layer structure, if you have those information, you will able to get XPS. I hope so. You understood what I am telling. The mainly XPS is for oxidation state analysis that you can't get from FTR and EDAX analysis. In FTR is completely different. So if there is no question, we'll stop here. So next class, Dr. Vinita, Madam, she will take the remaining lectures from the next Thursday, from the coming Thursday.